combustion reaction. In the case of combustion reaction, there's two approaches to solving the questions. The first approach is where you actually use equation balancing as a technique. You express the unknown x and y as a Stoichiometry constants in the equation. Then by using the data given in the questions, you can use proportionality and to formulate two simultaneous equations and then to solve it. That is technique one. Or what we want to focus on is to introduce the ice table as a technique for solving the question. So in these questions, it is given that 20 cm³ of your gaseous hydrocarbon undergoes complete combustion, which means the 20 cm³ is used up. And 150 cm³ of oxygen is initially added to the reaction. So in the ice table, the first row is the initial start state. And C is the chemical reactions that takes place. And E is the end state or equilibrium. So hence the acronym ICE. So to apply that for these questions, the 20 cm³ hydrocarbon is what is the start state for your hydrocarbon. The 150 cm³ is what is the start state for oxygen. And in this reaction, since it occurs at room temperature and pressure, and we are only studying the volume of gases, we don't have to consider water in these calculations since they are liquid. It starts with no products of complete combustion, so carbon dioxide ought to be 0. In the next part of the information, what they gave is that the reaction yields a total of 130 cm³ of gaseous products, which means at the end state, the total volume of all the gases add together is 130 cm³. Finally, they add to say that 90 cm³ is oxygen. So with that, we can fill up the 90 cm³ here, because that's the end state for the amount of oxygen that we get. And because this is 90 cm³, since we know that the gaseous hydrocarbon undergoes complete combustion, then we can conclude to say that there's 0 cm³ hydrocarbon left after the reactions. So in this case, the volume of 0 plus 90 plus this number must give me 130 cm³. And we can therefore conclude to say that this is 130 minus 90, which gives us 40 cm³. Once we fill up both the first and the last row, we can now focus on the chemical reactions. So if you start with 20 cm³ of your hydrocarbon and you end up with nothing, then 20 cm³ of the hydrocarbon must be used up. Because it's used up, we put a negative sign to connote that. In the same vein, if you start with 150 cm³ of oxygen and you're left with 90, therefore, in the chemical reactions, you should be using up 60 cm³. So again, we put a negative sign to connote that it has been used up. Finally, 40 cm³ of carbon dioxide is produced, and you start out with 0 cm³. So 40 cm³ of carbon dioxide must be produced in the chemical reactions, and because it's produced, we'll connote that with a positive sign. Once we obtain this ICE table, we can right away now balance the equation. Because if 20 cm³ of hydrocarbon reacts with 60 cm³ to give 40 cm³, therefore 1 mole of hydrocarbon must react with 3 moles of oxygen to give 2 moles of carbon dioxide. And from here, we can conclude to say that straight away, Y is equal to 2, since there's 2 carbon on the right side. Balancing the oxygen will allow us to put 2 next to the H2O, and from there we can conclude that X is 4. So hence we want to introduce the ICE table as a very quick technique for you to solve questions. Finally, let us now consider this example. We start out with a 10 cm³ hydrocarbon exploded with excess oxygen, RTP. Because it's RTP, we can ignore water. A contraction of 40 cm³ occur. On treating the products with sodium hydroxide, further contraction in volume of 50 cm³ occur. So the 2 pieces of data, first a contraction of 40 cm³. So first we can fill the table with 10 cm³ because that is the start state. Second of all, we know that oxygen is in excess. So quite clearly, it will be minus 10 and you will end up with 0. Next that we have is to look at on treating the products with sodium hydroxide, contraction of 50 cm³. There's a contraction of 50 cm³, that must be carbon dioxide. Since carbon dioxide is an acidic oxide that reacts with sodium hydroxide. We start off carbon dioxide with 0 cm³ and we end up with 50. Finally, the focus now will be on the row chemical reactions, because during the reaction, a contraction of 40 cm cube occur. It means the volume of this, the volume of hydrocarbon being used up, plus the volume of oxygen being used up, plus the volume of carbon dioxide being produced, must total to give you minus 40. So in this case, we can let, if we let this be x, then is minus 10 x is equal to, sorry, minus 10 plus x plus 50 is equal to minus 40. And from here, we know that your x, is equal to minus 80. Okay, so x is now minus 80. And once we actually obtain all that, we can now balance the equation, because if 10 cm cube of hydrocarbon reacts with 80 cm cube of oxygen, then that must be 1 mole reacting with 8. And that would end if 10 cm cube of hydrocarbon is used up and you produce 50 cm cube of carbon dioxide, then 1 mole must produce 5 moles of carbon dioxide. So x in this case will be 5. Now to balance the oxygen, that's 16 on the left hand side, 10 on the right, so I can put a 6 here to balance it. And by looking at the number of hydrogens on left and right, I can conclude this is 12.